What I want to do now is just go over some of the concepts and illustrate some of the content to hopefully make it a bit more sense to you. So vector concepts. So vectors are directed line segments, or they have magnitude and direction. So I'm going to start with two vectors. I'm going to call this one U, and a vector can be noted by a boldface or a little vector sign over it. And I'm going to call this one vector V. So both of these have a defined length or magnitude, and they definitely have some sort of direction. When we're working with geometric vectors, they just kind of float in space, and as long as I don't tilt them, I can move them around. I could redraw V as best as I could over here, and U. So let's look at vector addition. So this is when you put the two vectors together. Vector addition is basically tip to tail. So to do the first one, I'm going to start with U, and I'm going to reproduce it as best I can. So I've tried to match the length and direction of U. And then I'm going to now recreate V, but I'm going to recreate it starting at the tip of U. Because if we think of terms of displacement, if I'm looking at the displacement of U and V, which is U plus V, I would start there and there, then from there go to V. So now the resultant goes from the tail of the starting to the tip of the ending. So this vector represents U plus V. But I want to show you that order isn't important. Now I'm going to start with V first, and I'm going to draw it as best I can over here. I'm tipping it a little bit more than it did in the original, but pretend that I've kept the direction the same. So I'm going to start with V, and then I'm going to do U. So in this case, instead of doing U first, then V, I'm doing V first, then U. So my resultant in this case is V, then U. But if you look at these two vectors, and if I was able to draw with 100% accuracy, they are in fact the same vector. So this demonstrates the commutative property of vector addition, that U plus V is always the same as V plus U. The order of vector addition doesn't matter. Now I'm going to look at the next property, which was associative. So I'm going to start with three vectors. I'm going to call this one A, this one B, and that one C. So now I could look at A plus B plus C. So I would do A first, then I'd recreate B starting from the tip of A. Then I would recreate C, and the resultant, or my answer, would be A plus B plus C. But if you look at the laws, the one they said that A plus B, if I do those first because they're in brackets, and then add C, it's actually going to be the same as this, or the same as if I add B plus C first together, and then add A. So I'm going to look at this first. All I'm going to do is add A, then B, and I'm going to get my answer to that one. So now this just represents A plus B. Now to that, I'm going to add C, or I'm going to move it over so you can see I'm actually doing it separately. So there's my A plus B, which is my result from that. Here's my C, and then there's, if I add A plus B first, then add C. These two are the same. So if I add them all three together, or if I add two of them, take the answer and add the third, I get the same. And I'll quickly show that it doesn't matter which two you associate. That if I do B plus C first, So here's B. Put it where you can see it. So there's B. There's C. So then this vector represents B plus C. So then if I recreate that B plus C vector, and then I add my A to it, the answer that I get, again, is the same vector that I got when I just added the three of them without grouping two together first. If I grouped A and B together first, got an answer, then added C, or if I group B and C together first and then go back and add A, you get the same vector, the same result, and no matter what. So that's the associative property, that it doesn't matter if we associate two vectors together at the beginning and then proceed from there, you still get the same answer. But now I want to do some work with some actual numbers and letters with them. So example 1. U has a magnitude of 5. V has a magnitude of 8. And angle between them is 30 degrees. Find U plus V. So the important thing to remember is when you are looking for the resultant of vector addition, this is a vector. So we really have two pieces of information to find. We have the length or the magnitude, and we have the direction. In the first examples, when I was working with very geometric vectors that were just represented by line segments, they still had a magnitude or length and a direction, which was kind of the slant or slope they were on. In this case, we're given the magnitudes or the lengths, and we're given the angle between them. So this represents the direction. That means when I find my direction, I'm going to have to replicate this and give it as an angle. So the first thing I'm going to do is draw my vectors. So I'm going to make that U, so I know that this is length 5. I'm going to make that V, so I know that that's length 8. It's important to note that the angle between vectors is always given when they're tail to tail. So I know that that is 30 degrees. But in order to add vectors, they have to be tip to tail. So the triangle property or law for addition means I would slide U up here, and then my resultant would be right there. The parallelogram law for addition of vectors said I would move U up and replicate it there. I would move V over and replicate it there. But the addition is the diagonal of the parallelogram. So it doesn't matter if you just draw a triangle or if you draw the whole parallelogram, you're going to get the same answer. So now I know that that's 5. Here's the problem is I want this resultant here, so I need this angle. They didn't give me the angle between the vectors tip to tail. They gave me the answer between the vectors tail to tail. So I know that's 30 degrees. But the idea of a parallelogram does come into play here because these angles have to add to 180 degrees because it's half of a quadrilateral. Inside a quadrilateral is always 360 degrees. So inside half of it is going to be 180 degrees, and because this is a parallelogram, opposite angles have to be equal. So if that's 30 degrees there, I know that angle is 150 degrees. Now I want to use trigonometry, but this is not a right angle, so I can't use SOHCAHTOA. I'm actually going to use cosine law because I know two sides and the angle contained in between it. Or, more importantly, I don't have a pair or a set of information, so I'm going to use cosine law. So the magnitude of U plus V squared is the magnitude of U squared plus the magnitude of V squared minus 2 times the magnitude of V u times the magnitude of v times cos theta. But this theta represents the angle between them tip to tail. So then u plus v squared is going to equal 5 squared plus 8 squared minus 2 times 5 times 8 times the cos of 150 degrees. I'm going to type this into my calculator. Hopefully you have some experience with cosine law and you can type that into your calculator. Now, when I type it into the calculator and hit equals, that gives me the magnitude of u plus v squared. I just want the magnitude of u plus v, so I'm actually going to have to square root that. And of course I don't have my calculator. I'll be right back. Okay, so at least while I was walking, I typed it in, and I get 12.58 or 12.6. So now that's the magnitude of u plus v. Now I need the direction of u plus v. And now I'm going to reference it to either u or v. If I find this angle right in there, I'm going to label it alpha, that would give me the angle in between the resultant and v. That's an acceptable direction. If I find that angle, I know that angle, and I could give the direction to u. So when you're checking answers in the back of the book, don't panic if the direction doesn't match yours. They might be referencing the other vector. Take a minute to see if it makes sense. But now I have enough information to do sine law. So I have sine of my alpha, which is that angle, over 5 equals the sine of 150 over 12.6. Hopefully you know how to work sine law. I'm going to cross multiply, so I'm going to go 5 times sine of 150 divided by 12.6, but that's the sine of alpha. So then I'm going to inverse sine, which is the shift or second button, or maybe even the inverse button on your calculator. But when I shift sine, I get 11 degrees. So alpha is 11 degrees. So the magnitude of u plus v is 12.6, and there's 11 degrees between the resultant and v, which means that there are 19 degrees between the resultant and u. So the answer for direction could be quoted either way. You don't have to give both, you just need to give one, but I'm going to, therefore, u plus v has a magnitude of 12.6 and is 11 degrees to v, but you could have also said 19 degrees to u. The biggest thing when finding the resultant, students are very good at finding the magnitude, but they often forget to find the direction. Resultants are vectors. In order to be a vector, you have to have both magnitude and direction. So the last example I'm going to do is we're going to have a parallelogram. A, B, C, D. And we're going to look for AB, so the vector from A to B, subtract AD, and the first way we're going to do it is geometrically, and the second way we're going to do it is algebraically. I think I spelled that right. And then we're going to make sure our answers are the same. So now, these are point-to-point vectors. So AB is from A to B, so my arrow would be there. AD is from there to there, and now I'm going to subtract AD, which means actually do the opposite of AD. So if I think about this diagram, there's my AB, and subtracting AD is the same as adding the opposite of AD. Well, the opposite of AD is actually going to be that vector there. And because of the commutative property, I already have it set it up this way. There's the opposite of AD, there's AB, so my answer is going to be that, which is dB. So that's doing it geometrically. It's just working with the diagram, keeping these vectors floating, and just represent it. The opposite of AD and AB gives me from D to B. Now we're going to do it algebraically, and we're not going to need the diagram at all. So I'm going to start with the question, and I'm going to say, okay, this is the same as adding the opposite of AD. Well, an opposite vector has the same magnitude but opposite direction. So if I'm going from A to D, the way to represent the opposite direction is to go from D to A. So the opposite of AD is DA. Now I have AB plus DA, which doesn't really help me much. However, I notice a common thread here. I have A there and A there. The commutative property also says that I can switch this order. So instead of going AB plus DA, I'm going to go DA plus AB. So let's think about what this means. Start at D, go to A, then from A, go to B. So it really just represents a stop or a break at A. A is irrelevant there. If I could go from D to A and then A to B, my overall displacement is just from D to B. So algebraically, we are just working with the letters, moving things around, and whenever you have a letter back to back when it's adding, it really becomes just a pit stop, and you don't really need to think about it when you're doing replacement. So there's our answer DB, which matches it when we did it algebraically or thinking about the vectors.